Yeah.
I'm glad that everybody who's here is here. And so probably we should get started.
Okay.
You may have things that you want to do. So, I'm Larry Moss, and this is the Indiana University Logic Seminar. And I'm really pleased to have Siddharth Bhaskar back here. So Siddharth spent 2 years here, and his office is actually, I go by it all the time and think of him very often with a lot of affection. He had a good 2 years here, and we're sorry to see him go, but we see that he's in the midst of a very good career with work with people at his next position at Haverford College, and now in Copenhagen, where he's at the University of Copenhagen Computer Science Department, and holding forth on all matters of logic and complexity theory and foundational aspects of recursion theory, which he's quite expert in and is going to tell us about today.
Thank you very much, Larry. And it's a pleasure to be back in Bloomington, in some sense of the word back.
Yeah.
So today I want to talk about traversal invariant definability. And this is going to be a talk sort of in the intersection of descriptive complexity theory and model theory. And this is joint work with Steve Lindell from Haverford College and Scott Weinstein from the University of Pennsylvania, who might join us at some point. So in mathematics, this is a very common phenomenon. So we define a quantity, some quantity or some phenomenon in terms of some additional presentation of a structure, like additional information about a structure. But then we go on to prove that the quantity is independent or invariant of the specific presentation given. So some common examples of this are dimension of a vector space. So you can see I have a mixed media presentation here. So what is the most common way to define the dimension of a vector space? You pick a basis, and then it's the cardinality of that basis. And it doesn't matter what basis you pick, but to define it, we have to pick some basis. Another common example is the Euler characteristic of a surface. The Euler characteristic of these surfaces in 3 dimensions, are calculated by doing some triangulation or polygonalization of the surface, right? Something like I've indicated here. And then from that triangulation, calculating the number of vertices minus the number of edges plus the number of faces. And for a sphere, that's equal to 2, or something topologically equivalent to a sphere. For something topologically equivalent to a torus, that's 0, right? So here's another quantity which is defined in terms of some structure, but then actually turns out to be independent of that structure. And we want to study this phenomenon of presentation invariance model theoretically. And by the way, let me just interrupt myself to say, please feel free to ask any questions, interrupt me. As you can see, we're a very small group here. So yeah, so anything that you can think of, please feel free just to ask. So we want to study presentation invariance model theoretically. So this is how we're going to formalize this. We have 2 languages or signatures, L and L+. L is contained in L+. And we have a non-empty class of structures, P, which are L+ structures. And we're going to call these the presentations. And then like K, be the set of redux of P structures to L. So take every structure in P, take the L reduct, you get K. And then we say an L+ formula is KP invariant in case the semantics of the formula phi is identical on any 2 members of P which have the same L reduct. So if 2 different presentations share the same reduct in K, then the denotation of P is identical on those 2 presentations. And that's what it means to be KP invariant. You could choose to parameterize this with L and P instead of K and P, but for me, looking at the set of structures instead of the signature is more intuitive. So anyway, we're going to typically talk about first order presentation invariance, where the formula phi is a first order formula, but of course we could think of sort of any formulas from any logic. And now I'm going to define an invariance quantifier, right? So this is sort of a little bit of cheating syntax. So if we have this pair of classes of structures, K and P, and whenever I say K and P, it's always going to mean P is a non-empty class of structures, K is the set of L redux of P. So if you have a KP invariant formula, then such a formula actually takes on a semantics over K structures, right? Over structures in K, right? So we say that M satisfies PF of phi in case for some, that's a typo, in case for some, equivalently for all expansions of M in P, that expansion satisfies phi.
But you don't know that everything has an expansion, right?
No, we do, because K is defined to be the set of L redux of P. Yeah. So everything in K has an expansion in P, and everything and vice versa. Yeah. So once we have a KP invariant formula, basically this defines a query or a relation over K structures, even though it's in the language of P. And this invariance quantifier is just some syntax to make it happen. I use syntax here very loosely because whether or not a formula is a presentation invariant is typically a very undecidable, non-recursively enumerable sort of set of formulas. So there's not really, it's not syntax and sort of, it's not a logic in the sense of, is there a logic for P time? So that's going to probably prohibit us from doing proof theory, but it's not going to prohibit us from doing model theory, which is sort of the point of this talk. And what does the vector F represent here? The vector F sort of represents the non-logical symbols, which are in the expanded signature L plus, but not in the base signature L. And this invariance quantifier binds these. And you can think about it as a second order quantifier for that reason. Okay, so that's what I mean by an invariance quantifier. So for every pair of structures K and P, you have a different quantifier. So really we have an infinite class of these quantifiers. And then it's not hard to observe that the following properties hold of invariance quantifiers. So it's kind of silly, right? I mean, they just sort of commute with any first order logical operation, and or you can push a negation into or out of it, and they commute with taking the for all and exist quantifier. And so they're quite simple in that sense. However, presentation invariant, so invariant definability in general is stronger than first order definability. So a classic example of this is due to Yuri Gurevich. So in this case, let K be the set of all finite Boolean algebras, which you can think of as a set of finite power set algebras, and let P be the set of all expansions of K by linear orders. So take any finite Boolean algebra, expand it arbitrarily by a linear order. That's your presentation. So when we have when P is a set of expansions of K by linear order, we call this an order invariant logic, order invariant formula. So there is an order invariant way of defining the parity of a set of atoms of the Boolean algebra B, right? So by the set of atoms of a Boolean algebra set, theoretically, I mean the set of singleton sets, right? So of course, the number of sets in a power set is always even, but the set of atoms might be even or odd. And the idea is you could basically write a formula which asserts the existence of some set in the Boolean algebra which contains every other atom with respect to the ordering. And you can do this in a completely first order way. And this defines whether the set of atoms is even or odd. Well, even in this case. But the point is, it doesn't matter which ordering you take. It's completely, the semantics is completely independent of the ordering, but it's important that we have the ordering, right? So in an order invariant way, we can define the parity of the set of atoms over finite Boolean algebras. However, in a first order context, there's no formula simply in the language of Boolean algebras which defines the parity of the set of atoms. And you could see this in a number of ways, either by taking an ultra product or playing It's probably more elementary than this, but it's true. You can't do it simply in the language of Boolean algebras. So in general, presentation invariant definability is stronger than first order logic. However, under some conditions, KP invariant definability just collapses to first order definability over K. So for example, if P is an elementary class of structures, meaning the set of models of some first order theory, then anything which is any formula which is KP invariant is already definable by a first order formula over K. And this is essentially a restatement of the Bethe definability theorem. Another situation in which KP invariant definability could just collapse down to definability over K is when is if every structure in K has a uniform definitional expansion to some structure in P. So for example, if P is a set of all structures in K expanded by linear order, and K doesn't have a linear order, but you can define a linear order from the primitives of K uniformly over all structures in K, then anything which is order invariant over K is simply first order definable. You just take the linear order and you replace it by its first order definition. So these are two common situations in which the definability collapses. And how do we, in finite model theory, which is sort of where this idea comes from, how do they usually think about presentation invariant definability? Typically speaking, K is a set of all finite L structures, and then P is either something like the set of all expansions of K by linear orders. We call this order invariant definability. The set of all expansions of K by a successor relation. We call this successor invariant definability. And the set of all expansions of K by relational plus and times. So you identify the elements, each structure in K with the domain 0 through n-1, and on the domain 0 through n-1, you put relational plus and times. And there's no sort of standardized definition, I think, for this sort of invariant definability. And since K is a set of all finite L structures, which isn't an elementary class, we don't run into the sort of Bethe definability obstacle here. As you see, we can get proper extensions of first order definability. So are there any questions so far? Okay, so in this talk, what I want to talk about is a new form of presentation definability with respect to graph traversals over finite structures. And then I want to do the sort of descriptive complexity theoretic portion of this talk, which is connections to the complexity class L and NL, deterministic and non-deterministic logarithmic space, and then talk about some model theory, like extensions to arbitrary structures. So first, let me start talking about graph traversals. So a traversal of a finite connected graph is a linear ordering of its vertices such that the subgraph induced by each initial segment is connected. So, I'll go over some examples of this in the next slide. And we can extend this notion to disconnected graphs by basically saying that connected components have to induce intervals, and restricted to each interval is a traversal of its corresponding connected component, meaning that in each connected component, every vertex must have a preceding neighbor, except of course for the minimal vertex. And for finite graphs, there's actually a first order definition in the language of ordered graphs, which tells you when a particular ordering is a traversal. And it just says, for all vertices u less than v less than w, if u and w are connected by an edge, then v has a prior neighbor, right? So whenever you have a vertex v, which is sort of spanned by an edge, then it always has to have a neighbor before it. So for example, if you consider this professionally produced drawing of a force cycle with vertices labeled A through D, I've written down all of these 6 orders just for simplicity. Let's fix orders that start with A. And which one of these orders are traversals and which one of them are not. So it might be more instructive to look at the non-examples first. These are the ones underlined in red. So anything that starts with AC is not a traversal. And what's the reason for that? Well, AC is an initial segment of ACBD or ACDB. And the initial segment AC does not induce a connected subgraph of ABCD, right? Whereas for all the other four traversals, if you look at any initial segment of those traversals, they induce a connected subgraph of ABCD, right? So A, AB, AD, ABC, ABD, et cetera. These are all connected subgraphs. Another really nice way of looking at traversals is to draw, for each of these orderings, draw the least preceding neighbor function except for the least element. So for each element except for the least element, we can draw an arrow to its least preceding neighbor. So you can see that in ABCD, for example, the least preceding neighbor of B is A, the least preceding neighbor of C is B, and the least preceding neighbor of D is A. So least just meaning least with respect to the ordering. And you can see that an ordering of the vertices is a traversal if and only if the least preceding neighbor function is decreasing, right? So for each of these non-traversals, ACBD and ACDB, there is a vertex, namely C, in both examples, such that the least preceding neighbor is greater than C, right? So this is a really easy way to read off whether or not a particular ordering is a traversal. And so just some intuitions about traversals. Very connected graphs have lots of traversals. For example, if you take the complete graph, every permutation of the vertices is a traversal because the restriction that says that every vertex has to have a preceding neighbor and a connected component trivializes. In very disconnected graphs, there are also a lot of traversals because if you take, for example, the completely disconnected graph, well, each vertex is its own connected component, and we could sort of permute these arbitrarily, right? There's no restriction on how we order connected components. And so actually the graphs which have a few traversals are sort of the ones which split the difference. Something like connected acyclic graphs have very few. I should have said earlier that in this talk, all the graphs that I'm going to consider are undirected graphs. So let me say that now. So that's sort of some intuition. It's probably true that very connected graphs have a lot of traversals in some sort of either combinatorial or topological sense. I think this would be very interesting to investigate, but I don't know if that's true in some precise sense. Okay, and not only do we want to look at traversals, but we want to look at their restrictions, the refinements of breadth first and depth first traversals, right? So the first sort of definition of a traversal, looking at the bottom of the slide, is that in this situation where you have a vertex V, which is sort of between two endpoints of an edge, it has a prior neighbor. And the breadth first requirement basically says that in the situation where you have the vertex V between two endpoints of an edge, it has a prior neighbor actually prior to the first endpoint of the edge, prior to or equal to the first endpoint of the edge. And the depth first condition basically says that the prior neighbor of V, there exists a prior neighbor actually greater than or equal to the first endpoint of that edge. So looking at the set of traversals of this graph again, I don't want to apply that first order definition to each of these traversals, but just maybe take it on faith that the traversals ABDC and ADBC are breadth first traversals, and the traversals ABCD and ADCB are depth first traversals. This pink arrow here actually is the greatest preceding neighbor. The green arrow is the least preceding neighbor. And there are sort of conditions you can put on the arrows to check whether they're breadth first or depth first traversals. I think for now, I just want to appeal to your intuitions about breadth first search and depth first search, just to observe that if I were to breadth first search this graph starting at A, there's sort of two ways to do it. I start off at A, and then I have to discharge the neighbors of A before I get to C, right? So I either do BDC or DBC. And in a depth first search, I have to, from A, I go to either B or D, and then whichever of B or D I go to, first I go to C because it's the depth first search, and then I go to the remaining one of B or D, right? So hopefully you can see that these first order definitions satisfy your intuitions about what breadth first traversals and what depth first traversals should compute. So is that okay with everyone? Okay, I see two thumbs up from Larry, so
yeah,
proceed. Hey.
Standing up.
Yeah, okay, so I'll just briefly mention the connection to algorithms here. So really when I think about a traversal, I mean, I think there is a lot, there's not quite a precise meaning of traversal in the real world. Sometimes a traversal means the algorithm, and sometimes it means the order you compute. Here I'm using it strictly in the sense of the order that you compute, but I should at least mention that they're connected to these algorithms. So traversals are exactly the traces of the following non-deterministic algorithm. Pick a vertex V in your graph, initialize some set of vertices to that singleton vertex. Now, while the boundary of your set is non-empty, the boundary of the set means everything connected to the set but not inside the set. Pick an element of the boundary, add it to the set, and repeat. Okay, and that does it for connected graphs, and for disconnected graphs, whenever you're done with a connected component, just pick another vertex and continue until you're done, right? And then the order in which vertices are added to S is a traversal. And this is a non-deterministic algorithm because it says, you know, pick this, pick that. As you vary over all the traces of this non-deterministic algorithm, you recover the set of all traversals. And similarly for breadth first traversals and depth first traversals, and the corresponding refinements, breadth first search and depth first search, right? So if we change S, if we give S a Q structure, we get breadth first search. If we give S a stack structure, we get depth first search, roughly speaking. But it's still non-deterministic. And as we vary over the traces of those, we get exactly the breadth first and depth first traversals in this sense. Okay. So now we can talk about presentation invariant definability with respect to traversals. So let G be the family of all finite graphs, and let T be the family of all finite graphs expanded by a traversal, right? So it's like expanding it by all linear orders, but not all linear orders, just the ones which are traversals. Now we say a query, a subset of finite graphs, is basic traversal invariant in case it's defined by a traversal invariant sentence, such that, right, in other words, for any graph G and G, there's a typo over here. This should say G is in Q, not Q is in G, if and only if G satisfies the traversal invariant quantifier binding the less than relation of phi, right? So this math frac T is just the traversal invariant quantifier. And similarly, we have this notion of breadth first and depth first invariance definability, where instead of the presentation being all traversals, we just consider all breadth first traversals or all depth first traversals. So I should just make the observation here that traversal invariant definability is more powerful, or at least as powerful as order invariant definability, right? Because whenever I restrict the set of presentations, then I increase the number of formulas which are potentially presentation invariant, right? So it's sort of, you know, that's how the monotonicity goes, right? When I restrict the set of presentations, I increase the definability power. So when I restrict the set of presentations from orders to traversals, that's potentially stronger in expressive power. And when I restrict that further to breadth first or depth first traversals, those types of invariant definability are at least as strong as simple traversal invariant definability. Okay, so what kind of things can we define with traversal invariant sentences? For example, we can define connectivity, right? Which is well known as a sentence you can't define simply in the language of graphs, right? So a graph is connected, a finite graph is connected if and only if every non-minimal vertex has a preceding neighbor. Okay, and if every non-minimal vertex has a preceding neighbor, why is the graph connected? Let's just look in this direction. Well, pick any two vertices, v1 and v2. How do we know that there's a path between them? So we just basically take this least preceding neighbor function, the green arrow, and take the orbit of the vertex under this, right? So this bouncy green line is supposed to represent the orbits of v1 and v2 under the least neighbor function. It's always decreasing, and this is a finite linear order. So if you take two decreasing orbits in a finite linear order, eventually they have to intersect, right? If you just, you know, take v2 and bounce downwards and take v1 and bounce downwards, well, there's a point at which these have to stop. So at some point in time, the orbits have to intersect. And at that point in time, you've formed a path between v1 and v2. Another query that you can define with a traversal invariant sentence in a basic traversal invariant way is acyclicity, right? So G is acyclic if and only if in any traversal, equivalently all traversals, no vertex has more than two preceding neighbors, right? So if we have a cycle in a graph G, and then we linearly order a graph G according to a traversal, then of course, whatever element in the cycle is greatest is going to have two preceding neighbors. Conversely, if we have a vertex with two preceding neighbors, then what we can do is we can just follow those two neighbors under the least preceding neighbor function, and eventually they have to converge. So it's like this picture as if v1 and v2 were the same vertex, right? So if we had a vertex with two preceding neighbors, right? Imagine that as v1 and v2 in this picture over here, where they're identified. Then we have sort of two different orbits coming down from v1, equivalently v2, and then for the same reason, those two orbits have to intersect. Once they intersect, we have a cycle, right? And it doesn't matter what traversal we take. G is acyclic, right? With regards to any traversal, you're going to have a cycle if and only if you have a vertex with two preceding neighbors. So this is a basic traversal invariant query. Okay, and of course, acyclicity or cyclicity is also known not to be definable in the first order language of graphs, even over finite graphs. Isn't that so? I'm pretty sure. Okay, so are there any questions so far? Okay, so how do we extend? So we want a notion of traversal invariant definability, not just for graphs, but for arbitrary structures. And the way we're going to do that is we're going to close under interpretations. So recall that an interpretation is a map from a signature K to a signature L, which means that for every symbol, for every relation symbol in the signature K, we have an L formula with some conditions about the arities, which I'm not going to get into. But in an interpretation, if we have an interpretation from the signature K to the signature L, that actually gives us a map in the other direction from L structures to K structures. So I guess it's some sort of contravariant functor. And if we have a map from L structures to K structures, then via pullback, this actually gives us a map from K queries to L queries. Here, a query is just a subset of K structures, and an L query is just a subset of L structures, right? So given a K query Q, you can define the L query Q super pi by the set of all L structures A such that the translation A pi is in Q. Okay, so if we have a map from the signature K to the signature L, this induces a map from K queries to L queries in the following sense. And then we can just say that a query of finite L structures is traversal invariant if and only if it is the pullback of a basic traversal invariant query, which is just the spectrum of a traversal invariant sentence under a first order interpretation from the language of graphs to L. And in this sense, in this way, we have made sense of traversal invariant definability over any set of finite structures. Now, what can we define with this? Well, for example, consider the interpretation from the language of graphs to the language of orders, which basically says that two elements U and V are connected by an edge if and only if U and V are distanced 2 apart in the order, or U is the least and V is the second greatest, or U is the second least and V is the greatest. This basically means connect 2 vertices by an edge if they're 2 apart, sort of modulo identifying the beginning and the end of the linear order, right? And this interpretation allows us to get a graph from every linear order. And so if you look at the linear order of 4 elements, you can see that the graph that it gets by connecting the first and third and the second and fourth elements is the disjoint union of 2 cycles. And you can see that if we take the linear order with 5 elements, then the graph that we get out of this translation is actually, well, we connect element 1 to 3, 3 to 5, 5 to 2, 2 to 4, and 4 to 1. So we actually get, if you trace all of that, a single cycle. And so you can see proof by example that if you have an even linear order, then the corresponding translation is a disjoint union of 2 cycles. And if you have an odd linear order, then the corresponding translation is a single cycle. So this means that the pullback of the, okay, so obviously 2 disjoint cycles disconnected, 1 single cycle connected. So the pullback of the connectivity query under this interpretation from linear orders to graphs is exactly the parity. So we can define parity of finite linear orders with a traversal invariant query. On the other hand, parity of finite linear orders is not order invariant definable. You could see this using Aaron Fuchs-Frasset games, or looking at looking at the limit structures of the family of all even finite orders and odd finite orders. It's not first order invariant definable. So this actually separates in general traversal invariant definability from order invariant definability. And so we have a genuinely new notion here. And we can actually, so the fascinating thing is that these, the notion of traversal invariant definability actually captures logarithmic space computation over queries, logarithmic space queries over families of structures with a successor relation. So if L is a class of finite L structures, and if it has a successor relation, then an L query is computable in deterministic log space if and only if Q is a traversal invariant query, and it's computable in non-deterministic log space if and only if Q is, there's a typo here again, is breadth first traversal invariant. So I haven't just identified L and NL here. The second bullet point here should be if and only if Q is breadth first traversal invariant. So we found this, quite fascinating, that you can actually get some sort of non-trivial complexity class by sort of encoding the computation in an invariant use of a single traversal. And we can actually, so I said, assume that the family of structures L has a successor relation. We can actually get rid of the successor assumption with an additional use of the successor invariant quantifier, but that's a technicality I don't want to get into here. And what's the idea of the proof? the idea of the proof is, given a non-deterministic log space query Q, or just a deterministic log space query Q, we show that it's traversal invariant by defining an interpretation which transforms the original structure into the configuration graph of the appropriate machine. So appropriate machine meaning something which computes L or NL queries over structures. And the interpretation will transform the structure into the configuration graph of that machine with input that structure. And then we decide whether this configuration graph encodes an accepting computation using either traversal invariant or breadth-first traversal invariant query. In the traversal invariant case, the query in question is undecided reachability, which is not actually so different from connectivity. I could have actually defined it in this talk. The proof in the query in the breadth-first traversal invariant case is a little bit more sophisticated. Well, it turns out you have to basically have to compute directed connectivity, but the way of doing that in a breadth-first invariant way is a little bit more sophisticated. But the structure of both of these proofs is similar. The interpretation gets you to a configuration graph, and using a traversal invariant or breadth-first traversal invariant query, you determine whether this configuration graph is a configuration graph of an accepting or rejecting computation. And actually, interestingly, the proof is rather elementary modulo some hard results in complexity theory as black boxes. So in particular, it uses log space universal exploration sequences due to Reingold, the proof that L is equal to SL. SL here is symmetric log space. And both directions of this are non-trivial. The proof that NL is closed under complements due to Neil Immerman. And well, okay, those are all the three things that it uses. And it's sort of surprising that it uses all these things, but sort of modulo that is rather elementary. And of course, one of the elephants in the room is what happens to depth-first traversal invariance. We have no idea what it captures or if it corresponds to a reasonable complexity class in the same way. We imagine that it must, but we don't know which one it is. I think a really good candidate would be to check whether you can decide a context-free language with a depth-first invariant query, because this is something which is plausibly they're not all in logarithmic space, and the configuration graph of a pushdown automata sort of seems amenable to definability with the depth-first invariant query. But I don't have any other specific ideas other than that. So yeah, we can sort of characterize these complexity classes in these ways, and we're really excited about that. So that motivates me to consider traversal and breadth-first traversal invariant definability over arbitrary structures. Because if we can understand them over arbitrary sort of infinite structures, maybe that would give us some tools for comparing L and NL, or at least maybe it would show that there are some obstructions to separating them, or something like this. At least it motivates studying these two definability types over arbitrary structures. But first, to do that, we have to extend the notion of traversal to infinite graphs. So is there a way to extend the notion of traversal to infinite graphs that preserves the same definitions of connectivity and acyclicity? So we can ask, what about just taking the previous first order definition, right? Saying that for any vertex V, which is in between two endpoints of an edge, it has to have a prior neighbor. Does that suffice as a reasonable definition of traversal over infinite graphs? And well, you can see that it fails to define connectivity. If you can read my scroll here, you can see that if you take this ordered infinite graph, which is basically the union of two cycles whose vertices are interleaved, this is obviously a disconnected graph. It's the, sorry, if I said two cycles, I meant two infinite paths, right? The two infinite paths are clearly disjoint connected components, but every vertex has a preceding neighbor. So the previous definition of connectivity does not work in this context. Similarly, our definition of acyclicity does not work. Here is a single infinite path whose vertices are ordered so. You can see that it is a traversal according to our definition, but it does not have the cycle, yet there is a vertex over here, the greatest vertex, which has two preceding neighbors, right? So it seems that the previous first order definition doesn't work, but it turns out there is a really easy fix, which I'm hoping that these two pictures suggest, which is just to insist that your traversal be well ordered. So if we insist that our traversal be well ordered, everything works out. So the same definition works for connectivity, right? A graph is connected if and only if every vertex, which is not the least vertex, has a preceding neighbor. Why does it mean the graph is connected? Take two arbitrary vertices, v1 and v2, and again, these green bouncy arrows are the orbit under the least neighbor function. You just follow the two orbits. Since it's a well order, you can't follow them arbitrarily long. They have to stop at some points. And when they stop, they have to intersect, right? Because there's no point that they can stop, right? So you keep following the orders until they intersect. And then if they never intersect, then they just stop at the least vertex, which means that they intersect at the least vertex, right? So if we insist that traversals have to be well ordered, the same definition, first order definition of traversal, works to define connectivity, and the same first order definition of traversal works to define acyclicity in exactly the same way as for finite graphs, right? Under this definition of traversal, we can just say a graph is cyclic if and only if there's a vertex with two preceding neighbors, right? If there's a vertex with two preceding neighbors, we take the two preceding neighbors and we take the orbits under the least neighbor function. For the same reason they have to intersect. It's a well ordered, so it has to intersect at some point, and the graph has a cycle. And the traversal algorithm, in which we pick a vertex and keep adding vertices for the boundaries, extends to infinite graphs by taking limits at limit stages, right? So we do exactly the same thing at successor stages. We start off with this vertex v naught, we keep adding vertices in the boundary, and then at limit stages, we just take the union of all the stages less than that. And we do this until we reach a fixed point. And notice that the traversals that we get out of this algorithm are well ordered because they're indexed by the stages at which they appear. And we compute exactly the well orders of G which satisfy this first order definition as we vary over non-deterministic traces of this algorithm. So for me, this is like very convincing evidence for the correctness of this notion of traversal, right? Take the first order definition of traversal and just insist that the underlying linear order be a well order. And actually, the very same thing works for breadth-first traversals. If we just take the same first order definition of a breadth-first traversal, but insist that the underlying order be a well order, then we get a similar bijective correspondence with traces of the breadth-first algorithm extended to infinite graphs. Depth-first is a big mystery. It is not clear that depth-first traversals, if there is even a coherence definition of depth-first traversals over infinite graphs. So both in the descriptive complexity theoretic component and in the extension to infinite graphs component, depth-first traversals are a big mystery. Okay, but in any case, we get a notion of traversal invariant and breadth-first traversal invariant queries over arbitrary structures, by just doing exactly the same thing that we did for finite structures. A query is traversal invariant in case it's the pullback of a traversal invariant sentence under an elementary interpretation. A traversal is BFT invariant in case it's the pullback of a breadth-first traversal invariant sentence under an elementary interpretation. Right. And this also motivates a generalization of order invariance from finite to infinite structures. We can say that a query is well-order invariant if it's the pullback of a well-order invariant sentence under graphs under an elementary interpretation. And you might say, hold on, well-order invariance doesn't require us to say anything about graphs, but thankfully it turns out to be equivalent to the following definition. Phi is a query Q is well-order invariant if and only if there is a well-order invariant sentence psi, which the query is a spectrum of. So we have these three notions of invariant definability over infinite or arbitrary structures. Well-order invariant definability is the weakest one, then traversal invariant definability, then breadth-first traversal invariant definability is the strongest one. And we want to figure out how expressive these are, because they could potentially say something about complexity classes in the finite case. Okay, so this investigation is still very preliminary. We want to study these logics from the perspective of abstract model theory, as pioneered by John Barwise at Indiana University. In particular, we want to ask questions like, what are their relationships to second order and infinitary logics? What do the spectra of these theories in these logics look like, right? So spectra meaning the set of models of a single sentence or the set of models of a theory. When are they categorical? Either categorical in an absolute sense or categorical relative to fixed cardinality. And when do they contain models of a particular cardinality, right? So I'm imagining analogs of basic questions in first order logic like Löwenheim-Skolem property, right? So in first order logic, well, when are first order theories categorical? When they have when they're complete and when they have a finite model, right? Otherwise, they're not categorical in an absolute sense, but they might be categorical for a fixed cardinality. And then if a first order theory has an infinite model, then it has infinite models in all cardinalities. But that might not hold for these logics. And in fact, it doesn't hold for these logics. So here's just a list of things that we know. All of these properties are rather straightforward to prove. There's nothing heavy going on here. Each of these logics is contained in the delta 1,2 fragment of second order logic. And this is just because we have delta 1,2 or pi 1,1 definitions of well orders. All of them express the quantifier, there exists finitely many. So this is a well-known logic in abstract model theory. I think this is like L of Q naught is first order logic augmented with the there exists finitely many quantifier. It's a very interesting question to me, like what other quantifiers these logics might subsume, right? Like I highly suspect that they don't subsume the quantifier there exists uncountably many, but I don't know for sure. The Löwenheim-Skolem number of each logic, of each of these logics is aleph naught. And this is just from the ordinary Löwenheim-Skolem theorem. If we take a arbitrary model and we want to get a elementarily or well-ordered elementarily equivalent countable submodel, we just apply the ordinary Löwenheim-Skolem theorem. And since the original, it just comes from the fact that if we have a structure which is well-ordered and do the Skolem construction, the Skolem hull, the resulting structure is still well-ordered. The Hanf number is greater than aleph naught for each of these logics, right? So by the Hanf number, I mean, how large of a model do you have to get before you get models of arbitrarily large cardinality? So for first order logic, if you have just a countably infinite model, you get models of arbitrarily large cardinality. But that's not actually true for well-ordered invariant logic, and therefore for all of the other logics as well. For example, the theory of the countable complete graph is categorical. Because we can say that the degree, the theory of any infinite connected graph whose vertices all have finite degree is categorical. So it turns out with a well-ordered invariant theory, there are, we can describe this structure exactly up to isomorphism, which means that the Hanf number is not Aleph naught, but it is plausibly Aleph 1, and I have no idea what it is. Like, to me, this is like one of the central questions in measuring how powerful these logics are. And then the hope is by studying these logics, we can learn something about the L versus NL problem. And hopefully the sort of philosophy is like, with the machinery of abstract model theory, right, it will shed some light on the finite case, right? Like, if we can separate the Hanf numbers of traversal and breadth-first traversal invariant logic, or if we can't separate them, that might not suffice to separate or identify L versus NL, but I think at least it will like say something quite interesting about them. Okay, so that's it. Thank you very much, and I'd love to stay and chat a little bit. And yeah, thank you, Larry.
Thanks so much, Siddharth. I had a couple of questions, but I think other people might go ahead first. So go ahead, anybody who would like.
I had a question, Siddharth. It's good
Yeah.
to see you. The finitely many quantifier.
Yeah.
So how does that go?
So basically, it comes from this observation that in a well order, you can tell whether a how does that go? So the only well order without a limit point is omega. But what does that have to do with anything? It's not hard.
Okay.
I guarantee you that.
We can email later.
Yeah, I'll email you later. Maybe could you send? Is there a chat here or something?
Yeah, and I'll just send you an email, I think. Yeah.
Okay.
Anybody else? Well, I had a question. I mean, you had a long list of things at the end, but you didn't have things like whether adding the new quantifiers to the logic left it with, let's say, computably enumerable, validity problem, or satisfy, like what does that do to the basic questions of logic? Like, would logic have a complete axiomatization? This kind of question, like what is the complexity of the valid sentences?
Like the satisfiability relation?
Yeah.
Good question. I have no idea.
This is not where it's at for you, because you're interested in like using this to separate L and NL.
Yeah, but it's still very interesting, actually. I mean,
I thought it was an interesting. It's an interesting direction to think about these things.
Yeah. I mean, actually, one could probably, like, there's probably a, I mean, I wonder if you could say that, for example, the complexity of the satisfiability relation is different in some sense or in some context than first order logic.
Yeah, that's what I mean.
This would be very interesting.
Yeah.
No, I mean, I haven't thought about that at all, but that's very interesting.
I mean, I think, well, yeah. You also started out with with things in other areas of math, like
Yeah.
vector spaces and topology. Is there any hope of using these kind of ideas to illuminate that stuff in any way?
Well, I don't think that there's any connections to vector spaces or topology in particular. I mean, presentation invariant definability really comes up in descriptive complexity theory because we care about presentations of finite structures, right? Structures, and we want to consider Turing machines in the original formulation, which operate over encodings of structures, but whose the queries that they define are invariant or are identical on. So it comes up very naturally in this context. I really don't know if there are any applications. I mean, like they're very plausibly applications to something like geometry, and defining, maybe it's true that the Euler characteristic of the surface is definable in some invariant sense, but not in a first order sense. But then that would be very interesting to me. Steve, do you have any comments on this?
Well, not about the applications to other things in mathematics. My guess is that what Siddharth, I believe, is saying in this, and I'm sorry I missed the very beginning of the talk, is that the notion of invariant definability is sort of ubiquitous in mathematics, in the same way that Giannis would argue that inductive definability is also, and did so in his book.
Yeah.
What I find fascinating is Larry's comment that we could just view this as a logic and look at validity and satisfiability and all these other, recursive enumerability of syntax, all this stuff. Those are great. That's great, because I think Siddharth and I and Scott were excited when we thought, oh, we can do this in the transfinite if we just do well orderings.
Oh yeah.
And Siddharth just sort of moved ahead with that at great speed when he was visiting at Haverford. And that was really exciting to see how this notion naturally generalized in a very nice way. But now that it has generalized, I guess the obvious next question, Larry is right, is what is this as a logic?
Right. I had another point about your examples, Siddharth. So another example is like in your study group theory.
Yeah.
You worry about whether a permutation is even or odd. And that means it could be written as an even or odd number of transpositions.
Yeah.
But it might be a different number, like, so
Yeah.
to prove that that's well defined is not trivial.
No.
Sort of a hassle. So is it possible that some of the methods here could like give you sufficient conditions that could be usable in a math setting that would like imply results that get used all the time?
Well, I mean, here we don't have anything to say, so to speak, about whether or not a first order sentence is invariant, is presentation invariant, right? We just sort of use the fact that it is, or we have to show it. So, I don't think that this would give us any like new techniques for showing that the definition of the pair, what is it called, of a group, the sign of a permutation.
The sign of a permutation.
Yeah, whether this, like, it wouldn't give us any new techniques for proving whether the sign of the permutation is even or odd.
No, I meant to prove whether that notion is well defined, which is not sort of trivial. I mean, you have to do some.
No.
Okay.
I don't think it would give us any new tools to do that. No, but it might say something. I mean, like, it's an interesting question in group theory. I guess to say whether the first order theory of groups, or maybe some sort of special set of groups with additional constants naming generators or something like this, is more or less powerful than right? Is there directly is there directly a definition of the sign of a permutation sort of directly in the language of group theory? I mean, probably not, right? Otherwise, so actually this is probably a good example of something from the real world, which of this sort of phenomenon of getting strictly more things.
There's tons of things where you have to coordinatize some structure.
Yeah, exactly. Yeah. Yeah. So I think it would be like a very interesting program of going through these examples in real world mathematics and seeing like in what contexts are these sort of formalizable in some natural logic, and when do these formalizations give us something which is actually greater in expressive power, right? Like how much of group theory is, or whatever, is like the pure first order theory of groups, and how much is how much goes beyond that.